Hello there, and welcome to the Scientist Sleepy. Have you ever paused in the quiet moments and wondered why time, this ever-present force, seems to march so steadfastly in only one direction? Why does the universe unfold from past to future, never the other way around? Tonight, we embark on a gentle investigation into this profound mystery, exploring the fundamental principles that govern the direction of time, a concept that shapes our very existence. As you settle in, perhaps finding a comfortable position, allow yourself to sink deeper into this moment. If these explorations resonate with you, consider a gentle like and subscribe to join our community of quiet wonder seekers, ensuring you don't miss future journeys into the cosmos. And as you listen, perhaps you'll feel inspired to share your own thoughts in the comments below, a personal reflection on how the concept of time's directionality touches your own experience. Let us now turn our attention to the subtle, yet powerful arrow of time. The arrow of time, a cosmic mystery. We often speak of time as a river, flowing ceaselessly onward, carrying us from the past, through the fleeting present, and into the unknown future. But have you ever paused to consider why it flows only in one direction? Why can we recall yesterday with clarity, but the moments to come remain shrouded in uncertainty? This unidirectional nature of time, this fundamental asymmetry we experience, is one of the most profound and captivating mysteries in all of science. It's not merely a quirk of our perception. It's deeply woven into the fabric of the universe itself, influencing everything from the smallest subatomic particles to the grandest cosmic structures. Our journey tonight will delve into this extraordinary phenomenon, exploring the scientific principles that suggest time's relentless march forward is not an accident, but a fundamental characteristic of reality. It's a concept that can, at first, feel unsettling. This idea that the universe itself is constantly moving away from a state of perfect order. But within this grand narrative lies a profound sense of perspective and an invitation to embrace the present moment. We will unravel the threads of this cosmic mystery, not to find a simple answer, but to deepen our appreciation for the intricate dance of existence. The universe, as we observe it, exhibits a remarkable asymmetry with respect to time. This asymmetry is often referred to as the arrow of time. It's the reason why we remember the past but not the future, why broken eggs don't spontaneously reassemble, and why the universe itself seems to be evolving from a state of greater order to one of lesser order. This concept is not a mere philosophical musing. It's a cornerstone of our understanding of physics, particularly thermodynamics. The second law of thermodynamics, arguably one of the most fundamental laws in physics, states that the total entropy of an isolated system can only increase over time, or remain constant in ideal cases where the system is in a steady state or undergoing a reversible process. Entropy itself can be understood as a measure of disorder, randomness, or the number of possible microscopic arrangements a system can have. Imagine a perfectly ordered deck of cards, all suits and numbers in sequence. This is a state of low entropy. If you shuffle the deck, the cards become disordered, the entropy increases. It is overwhelmingly more likely that a shuffled deck will remain shuffled than it is that it will spontaneously return to its original ordered state. The universe, on a grand scale, appears to be following a similar trajectory. At the very beginning of the universe, in the moments after the Big Bang, the universe was in an extraordinarily low entropy state. It was remarkably uniform, incredibly dense, and highly ordered. From this state of extreme order, the universe has been expanding and evolving, with entropy steadily increasing. This increase in entropy is what drives many of the processes we observe: the cooling of stars, the decay of radioactive elements, the mixing of gases, and indeed, the aging of all living things. The arrow of time, therefore, is intimately linked to the universe's tendency to move from states of low entropy to states of high entropy. It's a cosmic imperative, a fundamental directionality imposed by the very laws that govern the universe. Without this tendency for entropy to increase, the universe would be a very different and perhaps static place. The events we witness, the flow of causality, the very experience of time passing, are all, in a deep sense, manifestations of this inexorable increase in disorder. It is the universe's grand, unfolding story, written in the language of increasing randomness. And so, the arrow of time points not just forward, but towards a universe ever more spread out, ever more complex in its disarray, reminding us that even in the grandest cosmic narratives, change is the only constant, and our place within this flow is a whisper of wonder in an ever-unfolding present. The illusion of now, why our present is fleeting. Our perception of time, this seemingly constant, unwavering flow, is one of the most profound illusions we experience. We feel as though we are perpetually inhabiting a singular point, a razor's edge we call now. This now feels intensely real, the only moment truly existing, a fleeting present that is born and dies in the very same instant. Yet from a scientific perspective, this sensation of a distinct and singular now is far more complex, and perhaps far less substantial than we intuitively believe. The universe, in its vastness and intricate workings, doesn't seem to possess a universal, agreed-upon now that stretches across all of existence. Instead, our experience of the present is deeply personal, tied to our own frame of reference, our own journey through space-time. Imagine, if you will, two observers separated by a significant distance, perhaps traveling at vastly different speeds. According to the principles of Einstein's theory of relativity, their experiences of time, and therefore their perception of what constitutes now, will not be the same. For one observer, a particular event might be happening in their present, while for the other, that same event could have already occurred in their past, or is yet to happen in their future. This isn't a matter of them simply disagreeing on the time. It's a fundamental difference in their experienced reality, a consequence of the very fabric of space-time. Time is not an absolute, universal clock ticking in unison for everyone and everything. Instead, it is a relative dimension, intertwined with space, and its passage is influenced by motion and gravity. This means that the now you are experiencing, the very words I am speaking to you, are not necessarily simultaneous with the now of someone on a distant galaxy, or even someone moving at a different velocity on Earth. This relativistic understanding of time challenges our deeply ingrained notion of a singular, universal present. It suggests that the now is not a fixed point but a moving boundary, unique to each observer. The universe in this view is more like a vast, four-dimensional block, containing all of past, present, and future events. Our consciousness in its journey through this block creates the illusion of a moving now. We are like a spotlight moving along a vast landscape, illuminating only a small portion at any given moment, and convincing ourselves that only the illuminated portion truly exists. The fleeting nature of now is not a flaw in our perception, but rather a fundamental characteristic of how time itself operates within the grand tapestry of the cosmos. And so, this ever-shifting present reminds us that, Our individual experience of time is a personal journey through an infinitely larger, timeless existence. Entropy's unseen hand, the universe's inevitable mess. Imagine, if you will, the universe not as a perfectly ordered, pristine machine, but as a vast, cosmic workshop where things naturally tend to spread out, to mix, to become less organized. This tendency, this fundamental drive towards disorder, is what scientists call entropy. It's not a force in the traditional sense, like gravity pulling you down, but rather a statistical inevitability, a consequence of probabilities playing out on an unimaginably grand scale. Think of it as nature's gentle, persistent inclination to make a mess, to unravel intricate patterns, to turn concentrated energy into diffuse warmth. This isn't a judgment, mind you. It's simply how the fundamental laws of physics seem to operate. The universe began in a state of extraordinary order, a concentration of energy and matter so dense and so structured that it defied our everyday intuition. But that state was, by its very nature, temporary. Like a perfectly stacked deck of cards, given enough shuffling, and the universe has been shuffling for billions of years, the cards will inevitably fall into a more random arrangement. This is entropy at play. It dictates that in any closed system, the total amount of entropy will either stay the same or increase. It never, ever decreases. This means that processes that lead to greater disorder are far, far more probable than processes that lead to greater order. Consider a perfectly formed crystal. It takes immense energy and precise conditions to create such a structure. Left to itself, over time that crystal will erode, its atoms will vibrate more freely, and it will eventually break down into a less organized collection of molecules. Similarly, the very act of living, of building complex biological structures, is a temporary, localized fight against entropy. Organisms maintain their order by drawing energy from their surroundings and releasing heat, thereby increasing the entropy of the universe around them. This is why life, in a grand cosmic sense, is an inherently temporary phenomenon. It is a fleeting pocket of order in an ever-expanding sea of disorder. The universe, in its entirety, is on a one-way journey from a state of low entropy to a state of high entropy. This isn't a sign of decay or failure, but rather a fundamental characteristic of its evolution. It's the grand, slow, and inevitable unraveling of complexity. The more we understand entropy, the more we begin to grasp the deep, underlying directionality of the universe. It's the reason why time, as we experience it, moves forward. It's the invisible hand guiding the cosmic dance from order to chaos, from the concentrated spark of the Big Bang to a diffuse, eventual, and perhaps surprisingly peaceful equilibrium. The universe's grandest narrative is written in the language of increasing disorder, a gentle reminder that all things in their own time return to a simpler state. The birth of the universe was a moment of astonishing order. Imagine for a brief, almost unimaginable instant, the entirety of existence, all matter, all energy, all space, compressed into a point of incomprehensible density and temperature. This is the state from which our universe emerged, a singularity that defies our everyday understanding of physics. It's a concept so profound, so removed from our familiar experiences, that it can feel almost alien. Yet, this is where the story of time's arrow truly begins. The prevailing cosmological model, the Big Bang Theory, describes not an explosion asterisk in asterisk space, but the rapid expansion asterisk of asterisk space itself from this initial state. And what is truly remarkable, and central to our understanding of time's direction, is the extreme degree of order present at this very beginning. If you were to rewind the cosmic clock to trace the universe back to its absolute origin, you would find not chaos but a state of incredible, almost perfect uniformity. The early universe was remarkably smooth. The fluctuations in temperature and density, the tiny seeds from which galaxies and stars would eventually grow, were infinitesimally small. This initial smoothness is crucial. It represents a state of very low entropy, a condition of immense order. Think of it like an impeccably organized library, where every book is in its precise place, perfectly aligned. The early universe in its nascent moments was such a library, but on a scale encompassing all of reality. This extreme order at the beginning is what allows for the subsequent unfolding of complexity and, crucially, for the unidirectional flow of time that we perceive. Without this initial low-entropy state, the universe would likely have remained a uniform, featureless expanse, or perhaps dissolved into a chaotic, undifferentiated soup, long before any meaningful processes could unfold. The very existence of a past and a future, the very possibility of change and evolution, is rooted in this astonishingly ordered genesis. It's a cosmic paradox. From an infinitely dense point, a universe of such ordered potential was born, setting the stage for everything that was to come, and for the relentless march of time. This initial, almost perfect state of low entropy is the fundamental bedrock upon which the arrow of time is built, a silent, cosmic decree that order would give way to complexity, and that the universe would forever move forward, never back. And so, in the cradle of creation, time was gifted its singular direction by the universe's own exquisite, ordered birth. The second law of thermodynamics, nature's fundamental rule. Imagine, if you will, a perfectly ordered deck of cards, each suit in sequence from ace to king. Now, imagine shuffling that deck. The cards become intermingled, their original order lost. This simple act of shuffling, though seemingly trivial, is a profound illustration of a universal principle that governs not just our decks of cards, but the very fabric of the cosmos, the second law of thermodynamics. This law, often described as nature's most fundamental rule, speaks to the inevitable tendency of systems to move from a state of order to a state of disorder, from a state of low entropy to a state of high entropy. It is the silent, unseen force that dictates the direction of change in the universe, the reason why time, for us, flows in one direction and one direction only. At its heart, the second law is about probability. In our shuffled deck, there is an astronomically vast number of ways the cards can be arranged, and only one specific arrangement represents perfect order. Therefore, any random process, like shuffling, is overwhelmingly likely to result in a disordered state. The universe, in this sense, is like an infinitely large deck of cards, constantly being shuffled by the ceaseless interactions of its constituent particles. Entropy, the measure of this disorder or randomness, is a concept central to understanding the second law. It's not simply about things becoming messy. It's about the dispersal of energy and matter. Think of a hot cup of coffee. Initially, the energy is concentrated in the coffee. Over time, this energy disperses into the cooler surroundings, and the coffee eventually reaches thermal equilibrium with the room. This process, the spontaneous flow of heat from hotter to colder objects, is a direct manifestation of entropy increasing. The energy doesn't vanish. It simply becomes less concentrated, less available to do useful work. This increase in entropy is not a choice the universe makes. It's a statistical inevitability. For any system that is not isolated, And in the grand scheme, no system is truly isolated. There are always more ways for it to be disordered than ordered. This is why spontaneous processes, those that occur without external intervention, invariably lead to an increase in the total entropy of the universe. Consider the universe at its inception, a state of incredibly low entropy, a state of remarkable order. From this initial, highly ordered state, the universe has been unshuffling itself ever since. Galaxies form, stars ignite and eventually burn out, planets cool, and complex structures, while they may appear ordered locally, are ultimately part of this larger, inexorable trend towards greater disorder. The second law doesn't forbid the formation of order. A star forming is a local increase in order. However, the processes that lead to this local order, the gravitational collapse and nuclear fusion, generate far more entropy in the surrounding universe than is created by the local order. Thus, the net entropy of the universe always increases. It is this fundamental principle that imbues the universe with its temporal directionality. We experience time moving forward because the universe is constantly moving from a less probable, more ordered state to a more probable, more disordered state. The arrow of time, the fundamental asymmetry we perceive, is inextricably linked to the relentless march of entropy. It is the universe's most profound and unwavering law, a gentle but persistent reminder of nature's grand, unidirectional unfolding. The universe, in its grandest design, gracefully surrenders to a gentle, inevitable diffusion, a cosmic sigh of increasing randomness that paints the passage of all existence. From order to chaos, the universe's grand unraveling. Our universe, in its grandest cosmic ballet, is engaged in a perpetual, yet subtle journey from states of remarkable order to those of increasing disorder. This fundamental principle, known as the second law of thermodynamics, is not merely a scientific curiosity. It is the very engine driving the universe's evolution, dictating the direction of every process, from the cooling of a star to the formation of a memory within our own minds. Imagine, if you will, a perfectly arranged deck of cards, each suit and rank in its pristine sequence. This represents a state of low entropy, a highly ordered system. Now shuffle that deck. Each shuffle, each interaction introduces a degree of randomness, a step away from that initial, perfect order. The cards do not spontaneously reassemble themselves into their original sequence. The natural tendency is towards a more mixed, a more disordered state. This is the essence of entropy, a measure of disorder, of randomness, of the unavailability of a system's energy to do work. The second law states that in any isolated system, the total entropy can only increase over time, or remain constant in ideal cases where the system is in a steady state or undergoing a reversible process. However, in the vast, evolving universe, truly isolated systems are rare, and reversible processes are even rarer. Every interaction, every energy transfer, every chemical reaction, no matter how small, contributes to this inexorable increase in overall entropy. Consider the simple act of a hot object placed next to a cold one. Heat, which represents the kinetic energy of particles, will naturally flow from the hotter object to the colder one, seeking to equalize the temperature. This dispersal of energy, this movement towards uniformity, is a manifestation of entropy increasing. The energy that was once concentrated and capable of doing work in the temperature difference is now spread out, less available. This process is irreversible. The heat will never spontaneously flow back from the colder object to the hotter one, restoring the original temperature difference. It is like trying to unspill milk. The energy has dispersed, the order has been lost. This principle applies to the universe as a whole. In the immediate aftermath of the Big Bang, the universe was in a state of incredibly low entropy, an almost unfathomable degree of order. The matter and energy were packed into an infinitesimally small volume, a state of extreme concentration and potential. As the universe expanded and evolved, this initial order began to unravel. Stars formed, galaxies coalesced, and complex structures emerged, but these are localized pockets of increasing order, achieved at the cost of a greater increase in disorder elsewhere in the universe. The birth of a star, for instance, involves the gravitational collapse of vast clouds of gas and dust, a process that increases local order. However, the nuclear fusion within the star releases enormous amounts of energy, radiating outwards and increasing the overall entropy of the surrounding space. Even the formation of life, a pinnacle of biological order, is a testament to this principle. Life harnesses energy from its environment, processes it, and ultimately dissipates it as heat, increasing the entropy of the universe. The very complexity of living organisms is a temporary, localized deviation from the universal trend towards disorder, a deviation that is powered by this ongoing increase in entropy. Think of a sandcastle built on a beach. The act of building the castle creates a temporary, ordered structure. But the wind, the waves, the passage of time, these are all forces that will inevitably break down the castle, returning the sand to a more disordered state. The universe is like that beach, and the sandcastle is a fleeting moment of order in an eternal tide of increasing entropy. This relentless march towards disorder is not a sign of decay or failure, but rather a fundamental aspect of existence, a cosmic imperative that shapes the very fabric of reality. It is the unseen hand that guides the universe's unfolding narrative, a story written in the language of energy dispersal and the loss of accessible potential. The arrow of time, that persistent feeling that moments only move forward, is deeply intertwined with this fundamental tendency towards chaos. Every event, every interaction, is a step further away from a hypothetical, perfectly ordered past. It is the engine of change, the driver of evolution, and the ultimate arbiter of the universe's destiny. The universe is not running down in a negative sense, but rather transforming, evolving from a state of concentrated potential to a state of dispersed equilibrium. This grand unraveling is not a tragedy, but a natural, majestic process that imbues existence with its dynamism and its direction. And in this grand cosmic unraveling, we find the universe's relentless journey from pristine order to an ever-expanding state of gentle chaos, a movement that gives direction to all that is. The scars of time, how processes leave their mark. Consider, for a moment, the subtle yet profound ways in which the universe inscribes its history upon itself. Time, in its relentless forward march, does not simply pass by. It actively transforms, alters, and leaves behind an indelible record. This is not a passive observation of a clock ticking, but an active engagement with the physical evidence of change. Think of a pebble smoothed by the ceaseless caress of ocean waves, each ripple a whisper of countless tides. Or the ancient granite, weathered by millennia of wind and rain, its surface etched with the stories of geological ages. These are not mere accidents of nature. They are the tangible manifestations of processes, each an irreversible step in the grand tapestry of cosmic evolution. The fundamental principle at play here is deeply intertwined with the concept of entropy, the universe's inherent tendency towards disorder. Every interaction, every transformation, no matter how small, increases the overall entropy of the system. This increase in entropy is not something that can be undone, not without expending an even greater amount of energy. And even then, the original state is never perfectly replicated. It's like trying to unbake a cake. The ingredients are forever altered. The energy that was once concentrated and ordered is now dispersed, spread out, and less available for further work. This dispersal is the scar left by the process. When we speak of leaving a mark, we are referring to the creation of a new, more probable, and less ordered state. A star, in its magnificent combustion, fuses lighter elements into heavier ones, releasing immense energy. This process transforms the star's composition, leaving behind a chemical signature that tells us about its life and death. The light and heat that radiate outwards are themselves a form of entropy increase, carrying energy away from the star and dispersing it into the vastness of space. This dispersal is a form of time's signature. Consider the very act of living. Our bodies are constantly undergoing complex chemical reactions, breaking down food, building tissues, and eliminating waste. Each of these metabolic processes leaves behind byproducts, waste materials that are then expelled. These are the microscopic scars of our biological existence, the evidence of the constant, unidirectional flow of energy and matter through our systems. We are, in essence, walking, breathing embodiments of time's passage, our very being a testament to the irreversible nature of biological processes. Even the seemingly simple act of a river carving its path through the landscape is a profound example. The water, in its journey from mountain to sea, erodes the rock, transports sediment, and reshapes the terrain. Each grain of sand carried downstream, each layer of rock worn away, represents a moment in time, an irreversible alteration of the Earth's surface. The riverbed itself is a scar, a permanent record of the water's passage. The more vigorous the flow, the deeper the cut, the more pronounced the scar, mirroring the increasing entropy of the system. The formation of mountains, the slow drift of continents, the violent dance of tectonic plates, all are processes that leave behind colossal, enduring scars on our planet. These geological transformations occur over timescales that dwarf human comprehension, yet they are driven by the same fundamental principles of energy dispersal and entropy increase. The heat from the Earth's core, slowly dissipating outwards, fuels these grand geological dramas, each eruption, each earthquake, a forceful inscription of time's power. The formation of fossil fuels like coal and oil is another remarkable testament to time's irreversible processes. Over millions of years, organic matter, buried under immense pressure and heat, is transformed into concentrated sources of energy. This transformation is a one-way street. The complex organic molecules are broken down and rearranged into simpler, more stable hydrocarbons. The stored energy within these fuels is a relic of ancient sunlight, a snapshot of a past era, locked away by the relentless pressure of time and the absence of oxygen. Even the very air we breathe carries the marks of time. The oxygen we inhale was produced by plants through photosynthesis, a process that has been occurring for billions of years, gradually altering the Earth's atmosphere. The nitrogen, the carbon dioxide, the trace gases, each has a history, a story of transformation and dispersal. The composition of our atmosphere is a constantly evolving scar, a record of the planet's biological and geological past. In the realm of astrophysics, the scars of time are writ large across the cosmos. Supernova remnants, the explosive deaths of stars, leave behind vast, expanding clouds of gas and dust, their intricate structures a testament to the violent energies unleashed. These nebulae are the cosmic brushstrokes of stellar demise, indelible marks left on the fabric of space-time. The light from distant galaxies, traveling for billions of years to reach our eyes, is itself a scar, a photon's journey through the ages, carrying information about a universe that has long since changed. The very existence of complex structures, from the delicate wings of a butterfly to the intricate circuitry of a galaxy, is a consequence of processes that have occurred over time. These structures are not static. They are the result of ongoing transformations, each step leaving a subtle, yet essential, mark that guides the subsequent steps. Life itself is a process that builds order locally, but at the cost of increasing disorder in the surrounding environment, thus adhering to the overarching arrow of time. Ultimately, the scars of time are not a sign of decay, but a profound testament to the universe's dynamic and ever-evolving nature. They are the whispers of history, the echoes of past events, and the undeniable evidence that change is the only constant. Each mark, whether etched in stone, dissolved in water, or radiating from a distant star, tells a story of irreversible processes, of energy dispersal, and of the fundamental directionality of existence. And in these enduring marks, we find a quiet reassurance, a reminder that our own fleeting moments are part of a grand, ongoing narrative, a continuous unfolding that imbues even the smallest change with cosmic significance. The irreversible nature of cooking an egg reveals a fundamental truth about our universe. Consider the humble egg. Inside its protective shell, a marvel of biological engineering awaits. The yolk, a vibrant sphere of lipids and proteins, floats suspended within the albumin, the clear, viscous fluid we commonly call egg white. This pristine state, this initial arrangement of molecules, represents a state of relatively low entropy. The proteins are largely unfolded, their complex three-dimensional structures relaxed, allowing them to flow and interact with a certain freedom. The water molecules within are also in a state of high mobility. This is the raw egg, a system poised in a sense for transformation, but a transformation that once initiated cannot be easily undone. When we apply heat, a fundamental change begins to occur. The energy input, typically from a stovetop or an oven, causes the protein molecules within both the yolk and the white to vibrate more vigorously. This increased kinetic energy disrupts the delicate bonds that hold the proteins in their folded, functional shapes. As these bonds break, the proteins begin to unravel, a process known as denaturation. Imagine a tightly coiled spring being stretched out, or a complex origami creation being flattened. The long chains of amino acids that make up the proteins begin to extend, exposing previously hidden regions. These newly exposed regions are often chemically reactive, and they begin to interact with each other and with other molecules in the egg. This is where the magic of a cooked egg truly unfolds. In the egg white, the albumin proteins, primarily albumin itself, denature and then aggregate or clump together. They form a network, trapping water molecules and creating the solid, opaque structure we recognize as cooked egg white. This process is not simply a change of state. It is a profound alteration of molecular architecture. The once liquid, translucent albumin becomes a firm, white solid. Similarly, The proteins in the yolk undergo denaturation and aggregation, but to a lesser extent, resulting in a firmer, yet still creamy, texture. This aggregation is driven by the formation of new bonds between the denatured protein chains. These bonds are stronger and more numerous than the original intermolecular forces that kept the raw egg in its liquid state. The overall entropy of the system increases significantly during this process. The molecules are now more ordered in their aggregated forms, but the asterisk process of aggregation itself, the breaking of old bonds and the formation of new, more stable ones, is inherently irreversible. It's like unweaving a tapestry. You can break the threads, but reweaving them into the exact original pattern, with all its intricate details and tensions, is practically impossible. The heat energy that initiated this transformation is dissipated into the surroundings, and the system moves towards a state of greater disorder at a molecular level, even as the cooked egg itself appears more structured. The key here is the irreversibility. You cannot simply cool a cooked egg and expect it to revert to its raw, liquid state. The chemical changes are too profound. The protein networks have formed, the bonds have been established, and the energy that drove this change has been released. This is not a reversible reaction like dissolving salt in water, where you can evaporate the water and recover the salt. Cooking an egg is an example of a spontaneous process that moves towards a higher entropy state, a state from which it is exceedingly difficult, if not impossible, to return to the initial, lower entropy state. It's a small, everyday demonstration of a fundamental law of physics, a gentle reminder that the universe, in its grandest and smallest workings, tends towards a certain direction. The transformation of a raw egg into a cooked one is a microcosm of this cosmic imperative, a tangible, edible illustration of time's persistent, unidirectional journey. And so, the simple act of cooking an egg beautifully illustrates that some transformations are not meant to be undone, reflecting the universe's own unidirectional march. The unmixing of cream from coffee. Consider for a moment the simple act of preparing a cup of coffee. You pour the dark, rich liquid, a testament to the roasting and brewing process, into your favorite mug. Then, with a gentle swirl, you introduce a small amount of cream. Observe how the cream, initially a distinct white cloud, begins to diffuse, to blend, to become one with the coffee. It spreads, its edges softening, its color lightening, until the entire beverage takes on a uniform, warm hue. You can stir and stir, trying to recapture that initial separation, that pristine white swirl against the dark background, but it is a futile endeavor. The cream and coffee, once mingled, do not spontaneously unmix. They do not separate back into their original distinct states. This is not a matter of insufficient effort or a lack of technological prowess. It is a fundamental characteristic of the universe, a silent decree etched into the very fabric of existence by the second law of thermodynamics. The universe, in its grand, cosmic journey, has a preferred direction, a direction that favors dispersal, diffusion, and an increase in overall disorder. The unmixing of cream from coffee, or more accurately, the asterisk failure of cream to unmix from coffee, is a miniature, everyday illustration of this profound, overarching principle. It is a small, domestic echo of the universe's relentless march from order to chaos. The initial state, with the distinct cream and coffee, represents a state of lower entropy, a more ordered configuration. As they mix, the system moves towards a state of higher entropy, a more disordered, more probable configuration. This movement is not reversible by simply reversing the stirring action. The energy expended in stirring is dissipated as heat, and the molecules, once thoroughly intermingled, are in a state far more likely to remain so than to spontaneously resegregate. This everyday phenomenon, so commonplace it often goes unnoticed, is a powerful, tangible manifestation of a law that governs everything from the smallest subatomic particles to the vast expanse of galaxies. It reminds us that while we can influence and manipulate our immediate surroundings, there are deeper currents at play, forces that dictate the fundamental direction of change. The coffee, once creamy, is a perfect, albeit small, example of time's arrow, pointing resolutely forward, away from perfect separation and towards an ever-increasing, gentle blend. The simple act of a perfectly blended cup of coffee is a quiet, persistent whisper of the universe's unyielding journey towards a more diffused state, a state that feels, in its own way, like a gentle, inevitable embrace. The forward march of evolution is a one-way street. Evolution, the grand process by which life on Earth has transformed and diversified over billions of years, offers one of the most compelling examples of time's unidirectional nature. It is not a cyclical process, nor is it a random wandering. Instead, it is a relentless, forward-moving journey, driven by the fundamental principles of variation, inheritance, and natural selection, all occurring within the framework of an ever-advancing temporal dimension. Consider the earliest forms of life, simple single-celled organisms that emerged in the primordial oceans. These organisms possessed a basic genetic code, a blueprint for their existence. Over vast stretches of time, random mutations, small changes in this genetic code, introduced new variations. Some of these variations were neutral, offering no significant advantage or disadvantage. Others, however, conferred a subtle edge. Perhaps a slightly more efficient way to capture energy, a marginally better defense against environmental hazards, or a novel method of reproduction. These advantageous variations, under the constant pressure of natural selection, were more likely to be passed on to subsequent generations. The environment, in essence, acts as a filter, favoring those traits that enhance survival and reproduction. This is not a process that can be easily reversed. Once a complex organism, with its intricate systems and specialized organs, has evolved, it is exceedingly rare, if not impossible, for that lineage to de-evolve back to its simpler ancestral state. The genetic pathways, the developmental processes, the very architecture of the organism are the product of a long series of cumulative adaptations. Think of the evolution of the eye, a marvel of biological engineering. It did not appear in its current sophisticated form overnight. It began with simple light-sensitive cells, which gradually became more complex, developing lenses, irises, and retinas, each step building upon the last, driven by the selective advantage of better vision. This progressive complexity, this branching and diversification, is inherently directional. The fossil record provides an undeniable testament to this. We see a clear progression from simpler to more complex life forms as we move from older geological strata to younger ones. We do not find evidence of highly complex organisms suddenly appearing in the earliest rocks, only to be replaced by simpler forms later. The history of life is a narrative of increasing complexity and diversification, a continuous unfolding that moves inexorably forward. Even the extinction of species, while seemingly a step backward for those particular lineages, ultimately clears the way for new evolutionary avenues to be explored by the surviving forms. It is a process of constant change, of adaptation and innovation, all occurring within the relentless flow of time. The very concept of progress in evolution is tied to this unidirectional nature. While progress can be a loaded term, in evolutionary terms it refers to the increasing ability of organisms to adapt to their environment and exploit new ecological niches. This adaptation is a one-way process of refinement and specialization, a testament to life's ability to not only survive, but to thrive and diversify in a universe that is constantly changing. The genetic information that underpins life is constantly being rewritten, not erased and rewritten in the same way, but rather added to, modified, and built upon. This accumulation of genetic change, this inheritance of acquired traits over vast timescales, is what propels evolution forward. It is a testament to the universe's inherent dynamism, a demonstration that change is not only possible, but is a fundamental characteristic of existence, and that this change, at least in the realm of biological complexity, moves in a discernible forward direction. This intricate dance of life, forever adapting and transforming, is a profound illustration of time's unwavering passage. The relentless branching of life, from simple beginnings to breathtaking diversity, paints a vivid picture of time's irreversible journey. Memory's directionality, why we remember the past, not the future. Our experience of time is deeply intertwined with our ability to remember. We possess a profound capacity to recall events that have already transpired, to revisit moments from our personal histories, to access a vast archive of past experiences. Yet, this remarkable faculty is entirely unidirectional. We do not, as a rule, possess memories of the future. This asymmetry in our recollection is not merely a quirk of human consciousness. It is a fundamental aspect of how physical systems, including our brains, interact with the universe and its inherent temporal directionality. At its core, memory formation is a process of physical change. When we learn something new, when an experience imprints itself upon our minds, there are tangible alterations occurring within the intricate network of neurons that constitute our brains. These changes involve the strengthening or weakening of synaptic connections, the creation of new neural pathways, and the complex biochemical cascades that encode information. These are physical processes, and like all physical processes governed by the laws of thermodynamics, they tend towards increasing entropy. To form a memory, energy must be expended, and this expenditure inherently leads to a net increase in disorder in the surrounding environment, however minuscule. This is not a process that can be easily reversed or run in the opposite direction. Think of it like writing a letter. Once the ink is on the page, the process of writing has occurred, leaving a permanent mark. You can erase or destroy the letter, but you cannot unwrite the words. Similarly, the physical changes that constitute memory are a consequence of past events, a record etched into the fabric of our neural architecture. The universe itself operates under a similar principle. The second law of thermodynamics dictates that entropy, or disorder, in an isolated system always increases over time. This fundamental law provides a cosmic arrow of time, a directionality that permeates all physical phenomena. Our memories are a reflection of this cosmic arrow. They are the universe's way of recording its own history, of creating a narrative that unfolds chronologically. The very act of remembering is an interaction with the past, a retrieval of information that has already been written into the physical state of our brains. The future, however, remains unwritten, a realm of potentiality rather than actuality. It has not yet imprinted itself upon our neural circuitry. The formation of a memory requires a stable state to be altered. The future, by definition, is not yet stable. It is in a constant state of becoming. Moreover, the process of memory formation itself is inherently irreversible. Reversing the process would imply somehow undoing the physical changes that have occurred, returning the system to a prior, less ordered state, which is statistically improbable to the point of being practically impossible on a macroscopic scale. Imagine trying to unbake a cake. The ingredients have been irreversibly transformed through heat and chemical reactions. While one could theoretically break the cake apart, the original components are gone, their molecular structures forever altered. Our memories are akin to that baked cake, a record of a process that has already unfolded. The very nature of information processing in biological systems, and indeed in any physical system, is tied to this irreversibility. To encode information, the system must transition from a state of lower information content, or higher uncertainty, to a state of higher information content, or lower uncertainty, about a particular event. This transition, this act of becoming more certain about something that has already happened, is a process that consumes energy and increases entropy, thus pointing towards the past. The universe, in its grand, unfolding narrative, leaves behind these traces, these records, and our memories are a deeply personal and intricate manifestation of this universal phenomenon. The directionality of our memories, therefore, is not an arbitrary limitation, but a profound consequence of the fundamental laws that govern the cosmos, a testament to the universe's ceaseless journey from order to disorder, from possibility to actuality, leaving behind the indelible imprint of what has been. Our capacity to recall the past, a fundamental aspect of our conscious experience, is a direct echo of the universe's own irreversible journey through time, a constant unfolding that leaves its indelible mark upon our very being. The asymmetry of causality, cause always precedes effect. Consider, for a moment, the fundamental fabric of our reality, the very scaffolding upon which existence is built. We experience a universe where events unfold in a sequence, a grand, intricate dance where one moment leads inevitably to the next. This perceived flow is not merely an arbitrary observation. It is deeply intertwined with a profound principle known as causality. Causality, at its core, is the relationship between cause and effect, a principle so ingrained in our understanding that its reversal seems almost nonsensical, a violation of the very laws of logic and physics. In our everyday lives, this asymmetry is so ingrained that we rarely question it. If you drop a glass, it shatters. The shattering is the effect, and the dropping is the cause. The cause, the act of dropping, must precede the effect, the shattered glass. It is impossible, within the framework of our observable universe, for the glass to spontaneously reassemble itself and then leap back into your hand, only then to have been dropped. This unidirectional nature of cause and effect is a cornerstone of our perception and our scientific inquiry. It allows us to build models, make predictions, and understand the consequences of our actions. Without this fundamental asymmetry, the universe would be a chaotic, unpredictable realm where effects could manifest without any discernible preceding cause, or where an effect could, impossibly, bring about its own cause. This principle is not just a philosophical musing. It is deeply embedded in the laws of physics. For instance, the equations governing many physical processes are time-symmetric, meaning they would work just as well if time ran backward. However, when we introduce concepts like entropy or the thermodynamic arrow of time, the directionality becomes apparent. The increase in entropy, the tendency towards disorder, naturally aligns with the forward progression of cause and effect. A highly ordered state, like a perfectly intact glass, naturally tends towards a less ordered state, like shattered pieces, when subjected to an external force, the cause. The reverse, the spontaneous organization of disordered particles into a perfect whole, is statistically so improbable as to be considered impossible within the vast timescales of the universe. This principle of causality, where the cause always precedes the effect, is a fundamental constraint on how events can unfold. It provides a directional bias to the universe, guiding its evolution from one state to another. It is the silent, invisible conductor of the cosmic orchestra, ensuring that each note, each event, follows in its appointed order. Imagine a vast cosmic domino chain. Each falling domino represents an effect, triggered by the preceding domino falling, the cause. This chain can only move in one direction forward from the initial push to the final topple. The universe, in this sense, is a perpetual sequence of such chains, each link forged by the one before it. This is why we remember the past and not the future. Our memories are records of causes that have already occurred, leading to effects that have already manifested. The future, by definition, is the realm of potential causes yet to unfold and their yet to be determined effects. This unidirectional flow of causality is what allows for the very concept of progress, of development, and of learning. We learn from past causes and their consequences, shaping our future actions based on this established order. It is the bedrock of our rational thought, enabling us to understand the world and our place within it. The very act of scientific investigation relies on this principle. We seek to understand the causes behind observed phenomena, confident that if we can identify the cause, we can predict or even manipulate the effect. This confidence is rooted in the unwavering asymmetry of causality. It is this predictable, linear progression that allows us to build our understanding of the universe, brick by carefully placed brick, each one laid upon the foundation of what came before. The universe, in its grandest and most subtle workings, operates on this fundamental truth, that a cause must exist before its effect can manifest. This inherent directionality is not just a rule. It is the very rhythm of existence, the pulse that beats through the cosmos, ensuring a coherent and understandable unfolding of events. It is the silent, yet undeniable architect of our temporal experience, guiding us through the river of time with an unwavering, forward-flowing current. This fundamental asymmetry is what allows us to perceive a coherent narrative in the universe, a story with a beginning, a middle, and a sense of progression, even as the ultimate end remains a profound mystery. The relentless march of cause and effect is the very pulse of reality, a constant reminder that what has been done shapes what is yet to be. And in this unwavering sequence of cause and effect, we find a quiet reassurance, a sense of order in the vastness, that even as the universe unfolds, there is a fundamental logic to its progression, a gentle rhythm that allows us to find our footing in the flow of existence. The expanding universe, a universe growing older. Our universe, as vast and ancient as it appears, is not static. It is in a constant state of outward motion. This expansion, a fundamental observation in cosmology, is not merely a spatial phenomenon but a profound indicator of time's unidirectional flow. Imagine the fabric of spacetime itself as a balloon being inflated. Galaxies, like dots drawn on the surface of this balloon, are not moving asterisk through asterisk space, but rather the space between them is stretching, carrying them further apart. This cosmic inflation, first theorized by Alexander Friedman and later supported by Edwin Hubble's groundbreaking observations, revealed that galaxies are, on average, receding from us, and the farther away they are, the faster they recede. This observation is a cornerstone of the Big Bang model, which posits that the universe began in an incredibly hot, dense state and has been expanding and cooling ever since. This expansion is not a localized event. It is happening everywhere, simultaneously. Every point in the universe is moving away from every other point. This relentless outward surge means that the universe is continually increasing in volume, and with that increase in volume comes a decrease in density and temperature. It is a grand, cosmic process of cooling and thinning, a testament to the universe's journey from a state of extreme order and energy to a state of increasing dispersal and entropy. This expansion is not a temporary phase. It is an ongoing process that has been occurring for billions of years, and according to current models, will continue into the distant future. The light we receive from distant galaxies, stretched and redshifted by this expansion, is a direct echo of this cosmic journey, a tangible piece of evidence that the universe is, indeed, growing older with every passing moment. The very act of observing these distant lights is akin to peering back in time, witnessing the universe as it was eons ago, a universe younger and more compact than the one we inhabit today. This continuous outward push is an indelible mark of time's passage, a cosmic clock ticking with the expansion of space itself. It is a demonstration that the universe is not a finished product, but a dynamic, evolving entity, forever moving forward on its temporal trajectory. The farther we look, the further back in time we see, and the evidence consistently points to a universe that began small and hot and is now vast and cooler, a direct consequence of its unceasing expansion. This expansive nature is not just about distance, it's about age. The universe is not just getting bigger, it is inherently becoming older as it expands, a continuous unfolding of its temporal story. The universe's outward breath is the universe's own steady aging, a cosmic exhale that carries us all into a future ever more distant from our fiery beginning. The cosmic microwave background, a whisper from the dawn of time. Imagine, if you will, a moment so profound, so utterly foundational, that its echoes still ripple through the vast expanse of existence. This is not a story of ancient myths, but a tale etched into the very fabric of reality, a testament to the universe's beginning. We are speaking, of course, of the cosmic microwave background, or CMB. This faint, pervasive glow bathing all of space is not merely light. It is a snapshot, a fossilized whisper from an era when our universe was but a fraction of its current age, a searingly hot, impossibly dense infancy. For decades, scientists have meticulously studied this ancient radiation, piecing together clues that reveal the universe's earliest moments, its initial conditions, and the subtle, yet critical seeds that would eventually blossom into the galaxies, stars, and planets we observe today. It is, in essence, the oldest light we can possibly detect, a direct messenger from a time before any stars had ever ignited, before any complex structures had formed, a time when the universe was a homogeneous, incandescent plasma. The very existence of the CMB, its remarkable uniformity across the sky, with only minuscule variations, provides one of the most compelling pieces of evidence for the Big Bang theory. It's as if the universe, in its infancy, uttered a single, magnificent sigh, and that sigh, stretched and cooled over billions of years, is what we now perceive as this faint microwave radiation. Understanding the CMB is not just about looking back in time. It's about understanding the fundamental laws that govern our cosmos and how those laws, from the very beginning, have guided the grand, irreversible march of time. The subtle temperature fluctuations within the CMB, measured with extraordinary precision by missions like COBE, WMAP, and Planck, are not random noise. They represent the tiny density variations in the early universe, the primordial ripples that gravity would later amplify, drawing matter together to form the cosmic web we see today. These variations, though incredibly small, are the blueprints for all the structure that would ever exist. They are the whispers of destiny, imprinted on the universe at its birth, dictating the direction of its evolution. The CMB, therefore, is not just a passive observer of time's passage. It is an active participant in its unfolding, a constant reminder of the universe's origin and the inexorable forces that have shaped its journey. Its discovery and subsequent detailed mapping has revolutionized our understanding of cosmology, transforming it from a field of speculation into a precise observational science. It allows us to peer back to a time when the universe was a mere 380,000 years old, a mere blink in cosmic history, yet a period of immense significance. Before this epoch, the universe was too hot and dense for light to travel freely. It was an opaque fog. As the universe expanded and cooled, electrons and protons combined to form neutral atoms, a process known as recombination, and suddenly, the universe became transparent. The photons, which had been constantly scattering, were finally free to travel unimpeded, carrying with them the imprint of the conditions at that very moment. This is the light we detect today as the cosmic microwave background. Its temperature, now a frigid 2.7 Kelvin, is a testament to the immense expansion and cooling that has occurred over the past 13.8 billion years. The slight anisotropies, or variations, in the CMB are crucial. They tell us about the composition of the early universe, the relative amounts of dark matter, dark energy, and ordinary matter, and provide constraints on cosmological models. These tiny temperature differences, often measured in microkelvins, are the seeds from which all the structure in the universe has grown. They are the primal whispers that, over eons, have amplified into the grand symphony of galaxies and clusters we observe. The CMB is, in essence, the universe's oldest photograph, a relic from a time when the cosmos was a nearly uniform soup of plasma, and the subtle variations within that soup were the genesis of everything that followed. It's a profound connection to our cosmic origins, a constant reminder that our present reality is built upon the foundations laid in the distant, incandescent past. The journey of these photons, from their release in the early universe to their detection in our sophisticated instruments, is a journey through time itself, a silent, yet eloquent, testament to the unidirectional flow of cosmic history. This ancient light, traveling for billions of years, carries with it the story of our universe's birth, a story that, like time itself, only moves forward. This ancient whisper from the universe's infancy serves as a constant, serene reminder that every moment we experience is a consequence of an ordered past, a past that forever shapes the unfolding present. The role of information, how information dictates time's flow. Consider the universe, not just as a collection of particles and forces, but as an immense, dynamic tapestry woven from information. This perspective shifts our understanding of time, suggesting that its unidirectional nature, its relentless march forward, is intrinsically linked to the way information behaves and evolves. At its most fundamental level, time's arrow might not be an inherent property of spacetime itself, but rather a consequence of the universe's tendency to increase its informational complexity, or more accurately, to process and distribute information in an irreversible manner. This concept is deeply intertwined with the second law of thermodynamics, that pervasive principle stating that entropy, a measure of disorder or the dispersal of energy and information, always increases in a closed system. When we think of information, we often imagine bits and bytes, digital data. But in a cosmological context, information is far more encompassing. It refers to any property that distinguishes one state of a system from another. The position of a star, the spin of a subatomic particle, the arrangement of molecules in a gas, all these represent information about the state of the universe. The crucial insight here is that processes in the universe tend to transform ordered, concentrated information into disordered, dispersed information. Imagine a pristine, highly organized library. Initially, all the books are in their correct places, cataloged and easily retrievable. This is a state of low entropy and high informational order. Now, imagine a gentle breeze passing through the library, scattering pages, misplacing books, and generally introducing a degree of chaos. Over time, without any effort to restore order, the library will become increasingly disordered. The information about the original arrangement of the books is lost, dispersed, and becomes much harder to reconstruct. This physical analogy, while simplified, captures the essence of how information tends to degrade or spread out in a way that is difficult to reverse. The universe began in a state of remarkably low entropy, a state of extreme order. This primordial state contained a vast amount of potential information, but it was highly concentrated and structured. As the universe evolved, this order has been systematically transformed into disorder. Stars burn, galaxies collide, and energy dissipates. Each of these processes, on a macroscopic level, represents a net increase in entropy and a dispersal of information. The light from a distant star, once a concentrated beam, spreads out across the cosmos, carrying information about its origin but in a form that is far less accessible. The heat from a supernova, once a localized event, radiates outwards, becoming a faint whisper in the cosmic background. This irreversible spreading of information, this transition from a state where information is readily discernible and localized to one where it is diffuse and scattered, is what gives time its direction. Consider the act of observation or measurement. When we measure a system, we extract information from it. This act of extraction, in many physical theories, is not a passive process. It can influence the system, and crucially, the information gained is often in a form that cannot be perfectly used to reconstruct the prior state of the system. For example, if you record the trajectory of a billiard ball, you gain information about its path. But from that recorded path alone, can you perfectly determine the exact initial conditions of the ball before it was struck? Not with absolute certainty, due to inherent uncertainties and the irreversible nature of the collision itself. This fundamental asymmetry in information flow, that information about past states can be used to predict future states, with increasing uncertainty. But information about future states cannot be used to perfectly determine past states, is a cornerstone of why we perceive time moving forward. The universe, in its grand cosmic dance, is constantly processing information. It's like a colossal, self-organizing computer, but one where the computational steps are irreversible. Each interaction, each event, leaves an indelible mark, a subtle shift in the informational landscape. And these shifts are always in one direction. The past is encoded in the present, in the configuration of matter and energy, in the residual radiation, in the very fabric of space-time. The future, however, remains unwritten, a realm of probabilities and potential. This is not to say that the future is entirely unpredictable. Statistical trends and physical laws allow us to make predictions. But these predictions are based on extrapolating from the information we have about the past and present. We can't directly read the future's informational content because it hasn't yet been fully actualized or dispersed in a way that leaves a universally accessible record. The very concept of causality, the idea that every effect has a cause that precedes it, is deeply embedded in this informational asymmetry. The cause contains the information that, when acted upon, leads to the effect. The effect, in turn, contains information about the cause, but this information is often transformed, dispersed, and integrated into a larger informational context. Reversing this process, deducing the exact cause from the effect, is often a monumental, and in many physical scenarios, an impossible task. This is the essence of the arrow of time, as dictated by information. The universe moves from states of greater informational order and lower entropy to states of lesser informational order and higher entropy, a progression that is inherently unidirectional. It is in this constant, irreversible flow of information, from the concentrated to the dispersed, from the ordered to the disordered, that the steady, unwavering rhythm of time finds its deepest meaning. This constant, irreversible flow of information, from the concentrated to the dispersed, from the ordered to the disordered, paints time not as a river we are merely floating on, but as a fundamental process of the universe itself, a process of information evolution. The quantum realm's enigma, time at the smallest scales. At the very foundation of our universe, within the bewildering domain of quantum mechanics, the concept of time begins to blur and shift in ways that challenge our everyday intuition. We perceive time as a continuous, unwavering river, flowing relentlessly from the past, through the present, and into the future. But when we zoom in to the realm of subatomic particles, the very nature of this flow becomes profoundly uncertain. Here, the smooth progression we experience seems to fragment, and the directionality of time, the very arrow that defines our reality, appears far less absolute. In the classical world, cause and effect are neatly ordered. A billiard ball strikes another and the second ball moves. The cause, the initial impact, precedes the effect, the resulting motion. This is the macroscopic world we understand, a world governed by predictable laws. However, at the quantum level, things are different. The interactions between particles are described by probabilities and wave functions. The equations that govern these interactions in many instances are time-symmetric. This means that if you were to run the equations backward, they would still describe a valid physical process. Imagine a film of a quantum event. If you played it backward, it would look just as plausible as playing it forward. This is a stark contrast to our macroscopic world, where playing the film of a shattered vase backward would appear utterly nonsensical. This time symmetry at the fundamental level raises a profound question. If the basic laws governing the universe are, in many ways, indifferent to the direction of time, then where does the macroscopic arrow of time, the one we so clearly perceive, originate. One of the key ideas in quantum mechanics is the concept of measurement. When a quantum system is not being observed, it exists in a superposition of states, a probabilistic cloud of possibilities. However, the act of measurement causes this wave function to collapse into a single, definite state. This collapse is often considered an irreversible process, and it is here that some physicists believe the arrow of time might be introduced into the quantum realm. The act of observing, of interacting with a quantum system, forces it to commit to a particular outcome, thereby creating a definite past for that interaction. Furthermore, the concept of entanglement offers another intriguing perspective. When two particles become entangled, they are intrinsically linked, regardless of the distance separating them. Measuring a property of one entangled particle instantaneously influences the state of the other. This seemingly spooky action at a distance, as Einstein famously called it, also hints at a deeper, more complex relationship with time. While entanglement itself doesn't necessarily dictate a direction, the process of disentanglement, or decoherence, as it's known, is a process that tends to move towards a more disordered state, aligning with the broader principles of entropy. The quantum realm also introduces us to the peculiar nature of quantum fluctuations. Even in what we consider empty space, there are constant, fleeting appearances and disappearances of particles. These events are governed by quantum uncertainty, where energy can be borrowed for infinitesimally short periods. While these fluctuations are incredibly rapid and seemingly random, they are still subject to the overarching laws of physics, and their collective behavior contributes to the overall evolution of the universe. The very act of defining a moment in the quantum world is fraught with difficulty. Unlike our continuous experience of time, quantum events can be thought of as discrete packets of interaction. The energy exchange, the change in state, happens in quantized steps. This discreteness, while not directly providing an arrow, suggests that time at its most fundamental level might not be a smooth continuum, but rather a series of individual, interconnected events. The enigma of time at the quantum scale is a frontier of scientific inquiry, a place where our most cherished notions of past, present, and future are tested and redefined. It is a realm where the universe whispers its deepest secrets about the nature of existence, suggesting that time, much like everything else, is a far more intricate and mysterious phenomenon than we can easily grasp. In the quantum theater, the script of time is written in probabilities, and the director is observation, subtly nudging the cosmic play towards a future we can only anticipate. The arrow of time in particle physics. At the most fundamental level of existence, within the ephemeral dance of subatomic particles, the arrow of time reveals itself in subtle yet profound ways. It's not a grand cosmic sweep, but a whisper in the quantum realm, a signature imprinted upon the very interactions that constitute reality. We often think of time as a river, flowing steadily onward, but in particle physics, this flow can appear more like a series of discrete, almost instantaneous events, each leaving a trace that points to its origin. The fundamental forces that govern these particles, like electromagnetism and the strong and weak nuclear forces, are not perfectly symmetrical with respect to time. While some interactions might appear reversible if we only considered the basic laws of motion, the reality is far more nuanced, involving the creation and annihilation of particles, and the subtle but crucial role of quantum states. Consider the process of particle decay. A particle, like a muon, has a finite lifespan. It spontaneously transforms into other lighter particles. This decay is an irreversible process. The original muon ceases to exist, replaced by a new configuration of energy and matter. While the underlying quantum mechanical equations can, in some simplified scenarios, be manipulated to run backward, the actual observed phenomenon is always forward-moving. This directionality is deeply tied to the concept of entropy, the universe's tendency towards increasing disorder, even at this minuscule scale. Each decay event increases the overall entropy of the system. Furthermore, the very act of measurement in quantum mechanics, the observation of a particle's state, collapses its wave function, a process that is inherently directional. We can't unobserve a particle's state and return it to its prior superposition. This irreversibility, this inherent one-wayness, is a hallmark of time's arrow, even in the seemingly chaotic and probabilistic world of quantum particles. The exchange of virtual particles, the fleeting interactions that mediate forces, also carry a temporal signature. While the mathematical descriptions can be complex, the net effect of these interactions in a macroscopic system, when aggregated over countless events, contributes to the overall directionality we perceive. The weak nuclear force, in particular, exhibits a subtle violation of charge parity, CP symmetry, meaning that certain particle interactions are not identical if you swap particles with their antiparticles and reverse the direction of time. This CP violation is a crucial piece of the puzzle, suggesting a fundamental asymmetry in the universe that underpins our experience of time's forward march. Even the seemingly instantaneous creation and annihilation of particles in quantum field theory, while appearing to happen at a point, are governed by principles that ensure a consistent temporal ordering. The propagation of quantum fields themselves follows a directional path, dictated by the laws of causality. The universe, at its most elemental, seems to be built with a built-in directional bias, a preference for moving from a state of lower temporal ordering to one of higher. In the quiet hum of the quantum universe, even the smallest interactions bear the indelible mark of time's relentless journey, reminding us that every event, no matter how fleeting, contributes to the grand, unidirectional narrative of existence. The Wheeler-Feynman absorber theory proposes a universe in perfect harmony. Imagine, for a moment, a universe where every interaction, every ripple of energy, finds its perfect, symmetrical counterpart. This is the elegant vision offered by the Wheeler-Feynman absorber theory, a fascinating concept that attempts to reconcile the seemingly unidirectional nature of time with the time-symmetric laws of physics at their most fundamental level. At its heart, this theory, developed by John Archibald Wheeler and Richard Feynman, suggests that the universe as a whole acts as a perfect absorber of electromagnetic radiation. When a charged particle, like an electron, emits a wave of light, it doesn't just radiate outwards indefinitely into an empty void. Instead, according to this theory, that emitted wave travels outwards and eventually encounters countless other charged particles scattered throughout the vast expanse of the universe. These distant particles, in turn, absorb the incoming wave. But here's the truly profound part. The absorber theory posits that these distant absorbers simultaneously re-emit the radiation, not just forwards in time, but also backwards. This backward-traveling wave then converges on the original emitting particle precisely at the moment of emission, effectively canceling out the advanced wave that would otherwise propagate into the future. The result is that only the retarded wave, the one that travels forward in time, is observed. This creates a remarkable symmetry. The outgoing wave from a source is perfectly balanced by the incoming wave from the absorbers, which, in turn, is balanced by their own re-emission. It's a cosmic dance of cause and effect, where the future influences the past just as much as the past influences the future. But the net effect we perceive is a clean, forward-moving progression. This elegant solution bypasses the need to arbitrarily assign a direction to time within the fundamental equations of electromagnetism. Instead, the directionality we observe emerges from the collective behavior of the entire universe. It implies that the universe is not a collection of isolated events, but a deeply interconnected system, where every particle plays a role in shaping the temporal flow for every other particle. The theory suggests that the universe, in its entirety, acts as a single, coherent entity, ensuring that the electromagnetic interactions are always consistent and self-reinforcing. It's a vision of a universe that is not chaotic or random in its temporal unfolding, but rather one that is profoundly ordered and interconnected, with every action finding its inevitable, harmonious echo across the cosmos. This interconnectedness, this universal absorption and re-emission, is what ultimately leads to the smooth, forward motion of time that we experience. It's as if the universe itself is constantly smoothing out the temporal bumps and kinks, ensuring a consistent, predictable flow. The Wheeler-Feynman absorber theory offers a glimpse into a universe where cause and effect are not merely sequential, but intricately woven into a tapestry of mutual influence, leading to the emergent arrow of time we perceive. It paints a picture of a cosmos that is not just governed by laws, but that actively participates in maintaining a temporal equilibrium, a delicate balance that allows for the unfolding of existence as we know it. The very fabric of reality, from the smallest emission to the grandest cosmic structure, is engaged in this continuous, harmonious exchange. In this grand, interconnected cosmic ballet, every emitted light wave finds its perfect echo, harmonizing the past and future into the singular melody of our perceived present. The problem of the past hypothesis: why was the universe so ordered? Our journey through the enigmatic arrow of time brings us to a profound and perplexing question, one that lies at the very heart of our understanding of the cosmos: the problem of the past hypothesis. It is the observation that the universe, at its very beginning, was in a state of extraordinarily low entropy, a condition of remarkable order. And this, in itself, is one of the most significant puzzles in cosmology. We perceive time as a relentless march forward, an irreversible progression from a state of pristine order to one of increasing disorder, a process governed by the second law of thermodynamics. But why was that initial state so special? Why was the universe born in such a state of near-perfect arrangement? If the universe tends towards disorder, as the second law dictates, how could it have possibly begun in such a highly ordered configuration? Imagine a deck of cards, perfectly ordered by suit and rank. The natural tendency, if you shuffle it, is for it to become disordered. It is astronomically improbable for it to spontaneously return to its perfectly ordered state. Yet, the universe in its infancy appears to have been precisely that: a cosmic deck of cards, perfectly arranged. This initial condition, this past hypothesis, suggests that the universe started in an exceptionally rare and ordered state. It's as if the universe began at the bottom of a very deep valley, poised to roll down its slopes towards a more chaotic, higher entropy future. But what sculpted that valley? What force or principle set the universe on this particular trajectory? Scientists grapple with this question, exploring various cosmological models. Some theories suggest that the Big Bang itself was not a random event, but a consequence of some preceding, even more ordered state, perhaps a quantum fluctuation from a vacuum of immense potential. Others explore the possibility that our universe is but one bubble in a vast multiverse, and we simply happen to inhabit a universe with this particular initial condition. The very fact that we can ask this question, that we can observe and ponder the universe's ordered beginning, is a testament to the intricate and perhaps finely tuned nature of reality. The universe's initial low entropy is not merely an observation. It is a fundamental premise upon which our entire understanding of time's directionality is built. Without this ordered beginning, the arrow of time, as we perceive it, might not exist at all. It challenges our assumptions about randomness and probability on a cosmic scale, forcing us to confront the possibility that the universe's origin was not a mere accident, but a profoundly significant event that set the stage for everything that followed. The universe's ordered dawn is the silent, majestic architect of our temporal experience. The universe's ordered dawn is the silent, majestic architect of our temporal experience. The multiverse and the arrow of time. Does every direction exist? Imagine, for a moment, a grand tapestry woven not just with the threads of our universe, but with countless others, each a separate reality, each with its own unique unfolding of events. This is the compelling and, frankly, mind-bending concept of the multiverse. Within this theoretical framework, the question of time's unidirectional arrow becomes even more profound. If there are indeed an infinite or at least an immeasurable number of universes, each born from slightly different initial conditions, could it be that in some of these universes, time flows backward, or perhaps, in others, time does not flow at all, existing in a perpetual frozen present? The prevailing scientific understanding, deeply rooted in the laws of thermodynamics and the observed expansion of our own cosmos, strongly suggests that time, as we perceive and experience it, moves forward. The second law of thermodynamics, with its relentless march towards increasing entropy, provides a powerful arrow, a fundamental asymmetry that dictates the direction of physical processes. Even if a multiverse exists, and this is still a speculative idea, the very formation and evolution of these universes would likely be governed by underlying principles that imbue them with their own temporal directionality. The idea of a universe where time flows backward is not easily reconcilable with our current understanding of causality, where effects follow causes, and information propagates forward. While some theoretical models might entertain such possibilities, they often involve highly abstract and unobserved phenomena. The existence of an arrow of time in our universe, from the Big Bang to the eventual heat death, seems intrinsically linked to its specific physical properties and its initial state of low entropy. Therefore, even within a vast multiverse, it is plausible that each individual universe would possess its own consistent temporal arrow, determined by its unique genesis and evolutionary path. The notion of every direction existing simultaneously across all possible universes presents a philosophical and scientific challenge, as it would require a fundamental reevaluation of causality and the very nature of existence. For now, the evidence within our observable universe points to a singular, forward-moving arrow of time, a grand narrative unfolding in a consistent direction, even if the stage upon which it plays might be infinitely larger than we can currently comprehend. The concept of a multiverse, while fascinating, does not inherently negate the observed arrow of time within our own cosmic home. Instead, it prompts us to consider whether this arrow is a universal constant or a property specific to certain types of universes, like our own. The elegance of our universe's temporal progression, from a state of profound order to one of increasing diffusion, suggests a fundamental directionality that may, or may not, be replicated across all potential realities. The exploration of the multiverse pushes the boundaries of our imagination, but the observed reality of our own temporal journey remains a powerful guide. The unfolding of events, the accumulation of experience, and the very fabric of our memories are all testament to a universe that, for us, moves inexorably forward. In the grand cosmic theater, where countless universes might play out their unique dramas, our own is painted with the indelible brushstroke of a forward-moving time, a testament to the universe's inherent tendency towards diffusion and change. The subjectivity of time, our perception versus physical reality. The universe, in its vast and indifferent sweep, operates according to fundamental physical laws. We speak of time's arrow, of entropy's relentless march, of the universe's expansion, all suggesting a singular, objective directionality. Yet, our asterisk experience of time is a far more fluid and personal affair. The ticking clock on the wall, the cosmic clockwork of celestial bodies, these are external measures, but our internal clock, the one that dictates our lived reality, can often feel remarkably different. Think about moments of intense joy or profound engagement. Time seems to vanish, to evaporate. Conversely, periods of waiting, of boredom, of discomfort can stretch into what feels like an eternity. This discrepancy between external, physical time and our internal, subjective experience is one of the most fascinating aspects of consciousness. It suggests that while the universe may have a fundamental direction, our journey through it is colored by our own unique inner landscape. Our perception of time is not a passive reception of an objective reality, but an active construction, shaped by our emotions, our memories, our attention, and even our physiological state. When we are deeply absorbed in a task, our brains are highly active, processing information at a rapid pace. This intense cognitive activity can lead to a feeling that time has accelerated. We are so focused on the present moment, on the task at hand, that the passage of time itself becomes less salient. Our attention is directed outwards, towards the stimulus, and inwards towards the cognitive processing, leaving little room for meta-awareness of time's flow. On the other hand, when we are bored or anxious, our attention may turn inwards, focusing on the passage of time itself. We become acutely aware of every second, every minute as it ticks by. This heightened self-awareness, coupled with a lack of engaging external stimuli, can make time feel like it is crawling. Our internal state, our emotional valence, plays a crucial role. Fear, for instance, can make time seem to slow down, allowing our brains to process a perceived threat with greater detail. This is an evolutionary adaptation, a survival mechanism. In a moment of danger, the ability to perceive events in slow motion can provide precious extra milliseconds to react, to escape. Conversely, happiness and contentment can make time fly. When we are enjoying ourselves, we are less likely to be monitoring the clock. Our focus is on the positive experience, and the external measure of time fades into the background. This subjective stretching and compressing of time is not an illusion in the sense of being unreal. It is a real phenomenon of our consciousness. It highlights how our minds are not merely passive observers of the universe, but active participants in shaping our reality. This is why two people can experience the same objective duration of time in vastly different ways. A thrilling adventure might feel like it lasted only an hour, while a tedious wait in a doctor's office for the same duration can feel like days. The brain's neurochemical environment also contributes to this subjectivity. Neurotransmitters like dopamine, associated with reward and motivation, can influence our perception of time. Higher levels of dopamine are often linked to a faster subjective passage of time, while lower levels can lead to a perceived slowing. Furthermore, our memories are not recorded like a perfect video playback. Instead, they are reconstructed, and our recall of past events can be influenced by the emotional intensity of the experience. Highly emotional events, whether positive or negative, tend to be remembered more vividly and can sometimes feel as though they happened more recently than they actually did, further blurring the lines of temporal perception. The very concept of now is also a product of this subjective experience. While physics might describe a continuous flow of events, our consciousness experiences a series of nows, each fleeting and instantly becoming the past. This perceived present moment is a cognitive construct, a window of awareness that is constantly shifting. It's a delicate balance, where the objective march of the universe is filtered and interpreted through the intricate lens of our individual minds. This interplay between the external, physical reality of time and our internal, subjective experience is a profound reminder that our understanding of existence is not solely based on what is, but also on how we perceive and process it. It is a testament to the complex and wondrous nature of human consciousness, a realm where the grand cosmic clock is harmonized, or sometimes at odds, with the rhythm of our own beating hearts. Our inner world paints the passage of moments, proving that time, while a cosmic constant, is also a deeply personal journey. The psychological arrow of time, why we experience it linearly. Our minds, in their intricate dance with reality, construct a powerful perception of time's relentless forward march. This isn't merely a passive observation of the universe's grand entropic unfolding. It is an active, deeply ingrained feature of our consciousness. We don't just see events happening in sequence. We feel them. This feeling, this internal sense of duration and progression, is what scientists often refer to as the psychological arrow of time. It's the subjective experience that makes the past irrevocably gone, the present fleetingly here, and the future an unwritten expanse. This arrow is so fundamental to our being that it shapes how we understand ourselves, our memories, our decisions, and our very place in the cosmos. It's the reason we can recall a childhood birthday with vivid clarity, yet have no direct access to the moments that will define our lives years from now. Our brains are wired to process information in a way that reinforces this unidirectional flow. Consider the act of learning. We absorb new knowledge, building upon existing understanding. This process inherently moves forward. We cannot unlearn something. We can only add to it, modify it, or choose to ignore it. This constant accumulation of experience and information creates a temporal narrative within us, a story that has a beginning, a middle, and an anticipated, though unknown, end. Even our emotions are tied to this arrow. Regret, for instance, is a poignant acknowledgement of past events that cannot be altered. Anticipation, on the other hand, is a gaze towards a future that has yet to solidify. The very structure of our language reflects this. We use past tense verbs to describe what has happened, present tense for what is occurring, and future tense for what we expect or intend. This linguistic framework isn't just a tool for communication. It's a mirror of our cognitive architecture, a testament to how deeply embedded the unidirectional experience of time is within our very thought processes. Our perception of causality is also intrinsically linked to this psychological arrow. We understand that an action taken now will have consequences later, and we are accustomed to this sequence. The idea of a consequence preceding its cause is not just counterintuitive, it's fundamentally alien to our mental models of the world. This consistent experience of cause and effect, always unfolding from past to future, solidifies our internal sense of time's direction. Furthermore, our sense of self is built upon this continuous temporal thread. We are the sum of our past experiences, our present actions, and our hopes for the future. Without this perceived linearity, our identity would fragment, our narrative would collapse, and our ability to navigate the world would be profoundly impaired. The psychological arrow of time, therefore, is not just a passive witness to the universe's physical processes. It is an active constructor of our reality, a vital component of consciousness that allows us to make sense of our existence within the grand, flowing river of time. It is the internal compass that guides our journey, always pointing us forward, even when the destination remains shrouded in mystery. This internal clock, so deeply ingrained, is perhaps one of the most profound reflections of the universe's fundamental nature, a personal echo of the cosmic dance between order and chaos, between what was and what will be. And so, our inner experience of time, a constant stream of becoming, whispers the universe's secret story of inevitable forward motion. The biological clock, our internal rhythms in time. Within the intricate tapestry of existence, a profound and often unnoticed rhythm governs our very being. It is the biological clock, a marvel of internal timekeeping that orchestrates the symphony of life. This clock is not a singular entity, but rather a complex network of molecular mechanisms, genetic predispositions, and environmental cues that collectively dictate the ebb and flow of our physiological processes. From the gentle rise and fall of our body temperature to the precise timing of hormone release, from the deep, restorative sleep we crave to the energetic awakenings that greet the dawn, our biological clocks are perpetually at work, a testament to the universe's inherent propensity for ordered cyclical change. These internal pacemakers, often referred to as circadian rhythms, are deeply ingrained, influencing everything from our mood and cognitive function to our susceptibility to disease. They are, in essence, the whispers of the universe's grand temporal narrative playing out within the very cells that compose us, a constant, subtle reminder that we are not merely observers of time, but active participants in its unfolding. This internal timing system, honed over eons of evolution, allows us to anticipate and adapt to the predictable cycles of our planet, the rotation of the Earth, the waxing and waning of the moon, the changing seasons, ensuring our survival and prosperity within the larger cosmic dance. It is a testament to the universe's elegant design that even at the most intimate cellular level, the principles of temporal order are so profoundly expressed. As we delve deeper into the workings of this remarkable internal mechanism, we discover that our biological clocks are not merely passive responders to external stimuli, but active regulators of our internal environment. At the heart of these rhythms are specialized genes, known as clock genes, which produce proteins that oscillate in concentration over a roughly 24-hour cycle. These oscillating proteins, in turn, influence the expression of countless other genes, thereby controlling a vast array of physiological processes. This intricate feedback loop ensures that our bodies are optimally prepared for different times of day. For instance, During daylight hours, genes that promote alertness and metabolic activity are upregulated, preparing us for wakefulness and energy expenditure. As darkness falls, different sets of genes become active, initiating processes that conserve energy, repair cellular damage, and prepare the body for rest and rejuvenation. This finely tuned coordination extends to the release of hormones like melatonin, which signals to the body that it is time to sleep, and cortisol, which helps to wake us up and prepare us for the day's activities. The robustness of these rhythms is astonishing. Even in the absence of external cues like sunlight, our internal clocks will continue to operate, demonstrating their deep-seated biological imperative. This internal timekeeping is so fundamental that disruptions to these rhythms, often caused by modern lifestyles, shift work, or jet lag, can have significant negative impacts on our physical and mental well-being, underscoring the vital importance of aligning our lives with these natural temporal patterns. The very essence of our being is thus interwoven with the relentless, yet gracefully cyclical, march of time, a dance of order and renewal that defines our existence. Our biological clock, a constant whisper of the universe's temporal flow, reminds us that even in the stillness of night, life's grand rhythm continues its ceaseless, ordered progression, guiding us toward rest and renewal. The aging process is a biological manifestation of time's flow. Consider for a moment the intricate dance of life within a single cell, a microcosm of the grander biological narrative. Each living organism, from the smallest bacterium to the most complex mammal, is engaged in a continuous, relentless process of change, a journey dictated by the fundamental laws of physics and chemistry. This journey, at its most profound, is the experience of aging. It is not merely a passive decay, but an active, albeit often unseen, unfolding of a predetermined biological script. Our bodies are magnificent, complex machines, meticulously designed by eons of evolution, and like any machine, they are subject to the wear and tear of operation. This wear and tear, this gradual accumulation of subtle damage and the diminishing efficiency of repair mechanisms, is what we perceive as aging. It begins at the molecular level. Our DNA, the blueprint of life, is constantly bombarded by internal and external factors, leading to mutations and errors. While our cells possess remarkable repair systems, they are not infallible. Over time, these errors accumulate, affecting the cell's ability to function optimally. Proteins, the workhorses of the cell, also undergo modifications. They can misfold, aggregate, or become damaged, hindering their intended roles. Mitochondria, the powerhouses of our cells, become less efficient, producing less energy and more harmful reactive oxygen species, which further contribute to cellular damage. The telomeres, protective caps at the ends of our chromosomes, shorten with each cell division, acting as a biological clock that eventually signals the cell to stop dividing, a process known as senescence. Senescent cells, while not dead, are metabolically active and can release inflammatory signals that contribute to tissue dysfunction and chronic diseases. The immune system, our body's defense against pathogens, also undergoes age-related changes, becoming less effective at fighting off infections and more prone to chronic low-grade inflammation, a phenomenon known as inflammaging. This inflammation can damage tissues and organs, accelerating the aging process. Hormonal changes also play a significant role. As we age, the production of various hormones such as growth hormone, sex hormones, and thyroid hormones declines, impacting metabolism, muscle mass, bone density, and cognitive function. The extracellular matrix, the scaffolding that supports our cells and tissues, also changes. Collagen, a key structural protein, becomes less abundant and more cross-linked, leading to reduced skin elasticity, stiffer joints, and weakened blood vessels. The accumulation of senescent cells, the decline in cellular repair efficiency, the damage to DNA and proteins, the mitochondrial dysfunction, the hormonal shifts, and the changes in the extracellular matrix all contribute to a gradual decline in physiological function. This decline manifests in a myriad of ways, from the subtle loss of muscle strength and sensory acuity to the increased susceptibility to diseases like cancer, cardiovascular disease, and neurodegenerative disorders. It is a testament to the intricate, yet ultimately finite, nature of biological systems. The very processes that enable us to live, to grow, and to reproduce are, in their inherent nature, pathways that lead towards eventual decline. It is a fundamental aspect of being alive, a consequence of the relentless march of molecular events, each one a tiny step along the path of time. The body, in its very essence, is a chronicle of its own history, written in the language of molecules and cellular transformations. It is a profound and beautiful, albeit melancholic, illustration of existence's temporal nature. And so, we see that aging is not an external force acting upon us, but an intrinsic unfolding, a biological echo of the universe's own irreversible journey. The universe's ultimate fate is a profound contemplation, a vast canvas upon which the grandest scientific narratives are painted. Our journey through the arrow of time has led us to consider its potential endpoints, and one of the most widely accepted and perhaps most humbling is the concept known as heat death, or more formally, the Big Freeze. This isn't a sudden, cataclysmic explosion or implosion, but rather a slow, inexorable fading, a gradual descent into a state of ultimate equilibrium. Imagine, if you will, a universe that has reached a perfect state of sameness, where all energy has been evenly distributed and thus no more work can be done. In such a universe, temperature differences, which are the very engines of change and activity, would cease to exist. Everything would be uniformly cold, uniformly diffuse, and utterly still. This is the ultimate consequence of the second law of thermodynamics, the relentless march of entropy. Over unfathomable stretches of cosmic time, stars will burn out, galaxies will drift apart, and black holes, those voracious devourers of matter and energy, will eventually evaporate through Hawking radiation, albeit at an agonizingly slow pace. Even the fundamental particles themselves may eventually decay, if current theories about proton decay hold true. The universe in this scenario becomes a vast, cold, dark, and empty expanse, devoid of the vibrant, dynamic processes that characterize it today. There will be no more birth, no more death, no more change, because there will be no energy gradients to drive such transformations. The very concept of time, as we perceive it, tied as it is to change and the unfolding of events, would essentially lose its meaning. If nothing ever happens, then time, in a practical sense, stops moving forward. It's a future that is not violent but rather one of profound, eternal stillness. A universe where every atom is as far from every other atom as it can possibly be, and where the last vestiges of organized energy have dissipated into the void, leaving behind only a uniform, unchanging cold. This is the ultimate silence, the ultimate peace perhaps, but also the ultimate stillness. It is the final, quiet exhalation of existence, where the cosmic clock has wound down completely, and the arrow of time, having flown its course, finally finds its rest. And in this endless, quiet night, the universe finds its ultimate, unchangeable peace, a stillness that reflects the deepest calm we can ever imagine. Can time be reversed? The scientific perspective. The question of whether time itself, this relentless river flowing ever onward, could ever be coaxed to flow backward, has long been a staple of philosophical debate and imaginative fiction. From the fantastical notion of a time traveler rewinding their personal history to the grander speculation of the universe itself reversing its cosmic expansion, the idea is deeply alluring. Scientifically, however, the prospect of reversing time's arrow encounters significant and perhaps insurmountable hurdles. At the macroscopic level, the fundamental laws of physics, particularly the second law of thermodynamics, present a formidable barrier. This law dictates that in any closed system, entropy, a measure of disorder or randomness, will always increase over time. Think of a shattered glass. It's easy to break, but incredibly difficult, if not impossible, to reassemble perfectly. The universe, as a whole, is generally considered a closed system, and its entropy is constantly increasing. Reversing time would imply a spontaneous decrease in entropy, a movement from a state of greater disorder to one of greater order, which directly contradicts this foundational principle. Imagine trying to unburn a log or unmix cream from coffee. These are everyday illustrations of entropy's unidirectional nature. Even if we could, hypothetically, reverse the motion of every single particle in the universe, the act of doing so would itself generate more entropy, likely creating a net increase. At the subatomic quantum level, the picture becomes even more nuanced, and in some ways more suggestive of a potential for symmetry, but not true reversal. Many of the fundamental equations governing the behavior of particles, such as those in quantum mechanics and electromagnetism, are time-symmetric. This means that if you were to reverse the direction of time in these equations, they would still hold true. For instance, an electron scattering off another electron can be described equally well whether time is moving forward or backward. However, this symmetry is broken when we consider the combined effects of these interactions and the role of measurement. The act of observation or measurement in quantum mechanics is inherently irreversible. When a quantum system collapses into a definite state, that process is not time-reversible. Furthermore, even if the underlying laws are symmetric, the initial conditions of the universe, the incredibly ordered state at the Big Bang, seem to have dictated the direction of time we experience. This past hypothesis is a crucial piece of the puzzle. While individual particle interactions might be reversible in theory, the cumulative and irreversible processes that define our macroscopic reality, from the formation of stars to the aging of living beings, are driven by increasing entropy. Therefore, while certain fundamental equations might possess a theoretical time symmetry, the universe as we observe and experience it, governed by thermodynamics and the initial conditions of its birth, appears firmly locked into a forward march. The very fabric of cause and effect, memory, and the unfolding of events is woven with the thread of unidirectional time. Thus, while the equations might whisper of symmetry, the grand symphony of the cosmos plays a clear, forward-moving melody, a testament to the irreversible unfolding of existence. The philosophical implications of a one-way universe. Our journey through the unidirectional flow of time, this grand cosmic river, leads us now to a contemplation of its deepest philosophical currents. If time, as science increasingly suggests, is a fundamental asymmetry, a one-way street etched into the very fabric of existence. What does this mean for our understanding of ourselves, our choices, and the nature of reality itself? The universe, in its grandest, most fundamental operations, seems to be an irreversible process. From the initial, incredibly ordered state of the Big Bang, through the relentless march of entropy, to the eventual quiet cooling of the cosmos, the arrow of time points resolutely forward. This isn't merely a scientific observation. It is a profound existential truth that shapes our perception of everything. We are creatures born into a universe that remembers its past, but remains blissfully ignorant of its future. This inherent directionality imbues our lives with a unique significance. Every moment once past is gone forever, never to be reclaimed. This is not a source of despair, but rather an invitation to profound presence. If moments are fleeting, then the present moment, the only point where we truly exist and can act, becomes infinitely precious. The philosophical implications are vast. It suggests that our actions have consequences that ripple forward, shaping a future that is not predetermined in its details, but is nonetheless a consequence of what has come before. The concept of free will in a universe with a determined past and an open, yet consequentially linked, future, takes on a new dimension. We are not merely actors on a stage where the script is already written. Rather, we are co-authors, our choices contributing to the unfolding narrative. The irreversibility of time means that mistakes cannot be undone, but also that growth and learning are genuine possibilities. We learn from the past not by reliving it, but by integrating its lessons into our present actions. The universe's one-way journey also fosters a sense of shared experience. We are all traveling together downstream on this river of time. Our individual lives, though unique, are part of a larger collective story. This shared journey, marked by birth, growth, and eventual dissolution, connects us all in a fundamental way. The universe, in its ceaseless forward motion, teaches us about the nature of change itself. Change is not an anomaly, it is the very essence of existence. To resist change is to resist the fundamental nature of the cosmos. Instead, we are invited to flow with it, to adapt, to evolve, and to find beauty in the ephemeral. The one-way arrow of time, therefore, is not a constraint, but a canvas. It provides the structure upon which we paint our lives, our choices, and our understanding of the universe. It highlights the significance of each passing second, urging us to live with intention and awareness. The universe's relentless forward momentum whispers that every moment is a unique creation, a brushstroke on the canvas of eternity, never to be repeated, forever shaping what is to come. Finding peace in time's unidirectional flow. The profound realization that time, in its grand cosmic dance, moves relentlessly in a single direction, can initially feel unsettling. We often yearn for the ability to revisit cherished moments, to undo regrettable choices, or to glimpse the unfolding future with certainty. Yet this unidirectional flow, this inherent asymmetry, is not a limitation to be lamented, but a fundamental principle that underpins the very fabric of our existence and, paradoxically, offers a path to profound peace. Consider the universe itself. Born from a state of unimaginable order, it has been steadily moving towards a state of greater disorder, a process dictated by the inexorable march of entropy. This constant unfolding, this irreversible transformation, is the engine of all change, all growth, and all life. Without this forward momentum, there would be no evolution, no development, no stories to tell. Our very consciousness is built upon this temporal linearity. We experience the world as a succession of moments, each building upon the last, creating the tapestry of memory that forms our identity. The past is a landscape we can reflect upon, learn from, and carry within us, but it is a landscape we cannot physically re-enter. The future, while unknown, is a realm of potential, shaped by the choices we make in the present. This present moment, fleeting and ephemeral, is the only point of direct experience. To resist this flow, to constantly wish for a different temporal trajectory, is to invite frustration and anxiety. True peace, however, arises from acceptance. It comes from understanding that this unidirectional arrow of time is not a cage, but a current that carries us forward. It is the force that allows for novelty, for surprise, and for the emergence of beauty from chaos. The universe is a grand, unfolding narrative, and we are participants in that narrative, each moment a unique chapter that cannot be rewritten. This acceptance allows us to release the burden of what was and the anxiety of what might be, grounding us in the precious reality of the now. It is in embracing this irreversible journey that we can find a deep and abiding sense of calm, recognizing that our place in the cosmos is defined by this constant onward movement. The very irreversibility that can seem daunting is, in fact, what imbues our lives with meaning and purpose. Each experience, each interaction, is unique and unrepeatable, making it all the more precious. This understanding fosters a profound gratitude for the present, for the simple act of being, and for the continuous unfolding of existence. It allows us to let go of the illusion of control over time's passage and instead find solace in its inevitable, yet beautiful, progression. This acceptance is the quiet wisdom that allows us to navigate the currents of existence with grace, understanding that the journey itself, in its onward flow, is where true contentment resides. In the gentle, relentless current of existence, we find our peace not in resisting the flow, but in learning to dance with its unwavering, forward motion. Embracing the present, acknowledging time's constant movement. The present moment, this ephemeral sliver of existence we perceive as now, is the only point of contact we have with reality. It is the stage upon which all our experiences unfold, the canvas upon which our lives are painted. Yet, paradoxically, it is also the most elusive aspect of time. As soon as we try to grasp it, to pin it down and define it, it has already slipped away, becoming the past. This inherent transience is not a flaw in our perception, but a fundamental characteristic of the universe itself. Time, as we understand it through the lens of physics, is not a static river we can stand beside, but a ceaseless, unidirectional flow. Every scientific principle we've explored, from the relentless increase of entropy to the asymmetry of cause and effect, points towards this inescapable truth. Time moves, and it moves only forward. To truly understand why time moves only in one direction is to begin to understand the very fabric of our existence. It's to recognize that the universe is not a static snapshot, but a dynamic, evolving entity. This constant motion, this forward momentum, is what gives rise to change, to growth, to the very possibility of experience. Imagine a film reel, each frame a distinct moment, yet it is only when these frames are projected in sequence in a specific order that a story emerges. Our lives are much like that. The past provides the context, the foundation upon which the present is built. The future, though unknown, is a consequence of the present's actions. To resist this flow, to cling desperately to moments that have already passed, or to anxiously anticipate moments yet to come, is to fight against the very nature of reality. It is to miss the profound beauty and quiet wonder of the present, the only place where life truly happens. The universe is a symphony of change, and the present is the note being played right now, a note that will never be repeated in precisely the same way. Acknowledging this constant movement, this unwavering march forward, allows us to release the anxieties that often accompany our perception of time. It helps us to understand that the past is a lesson, not a prison, and the future is an unfolding possibility, not a predetermined doom. By accepting the arrow of time, we can find a deeper peace in the fleeting nature of each moment, recognizing its unique value and its integral role in the grand cosmic narrative. This acceptance can be a powerful antidote to stress, a gentle reminder that even in moments of difficulty, the current is carrying us forward towards new experiences, towards new understanding, and ultimately towards a deeper connection with the universe. The present is not a point to be held, but a current to be navigated, a gift to be received with open awareness. And in this ceaseless current, we find our anchor, not in holding on, but in the gentle art of letting go and simply being present with the unfolding now. The beauty of impermanence, a cosmic perspective on change. The universe, in its grand and silent unfolding, is a testament to the profound beauty of impermanence. It is a constant dance of creation and dissolution, of becoming and unbecoming, a symphony played out across the eons. We, as conscious observers within this cosmic ballet, often struggle with this fundamental truth. We cling to moments, to states of being, to the familiar, fearing the inevitable shift. Yet if we were to adopt a truly cosmic perspective, we might begin to see that this ceaseless change, this inherent impermanence, is not a source of sorrow, but of wonder. Consider the stars themselves. They are born from vast nebulae, coalescing under the immense force of gravity, burning brightly for billions of years, only to eventually exhaust their fuel and collapse, sometimes in spectacular supernova explosions, scattering their constituent elements across the cosmos. These elements, forged in the heart of dying stars, become the building blocks for new stars, new planets, and indeed, for life itself. The very atoms that compose our bodies were once part of celestial bodies that have long since ceased to exist in their original form. This cyclical nature, this constant transformation, is the essence of the universe. It is a process that ensures renewal, that prevents stagnation. If the universe were static, if everything remained as it is, there would be no evolution, no growth, no new discoveries, no unfolding of consciousness. Impermanence is the engine of progress, the fertile ground from which novelty springs. Think of the seasons. Each year, the world undergoes a dramatic transformation. The vibrant greens of summer give way to the fiery hues of autumn, then to the stark, quiet beauty of winter, only to be reborn again in the gentle blossoming of spring. Each phase has its own unique charm, its own lessons to impart. To resist the change of seasons is to deny the natural rhythm of life, to yearn for a perpetual summer, which, while perhaps appealing on the surface, would ultimately lead to exhaustion and decay. Similarly, in our own lives, the moments of joy are often made more poignant by the knowledge that they are fleeting. The comfort of familiarity is precious, but the prospect of new experiences, of learning and growing, is what gives life its depth and richness. The very act of remembering is an acknowledgement of impermanence. We hold on to memories, but the events themselves are gone, existing now only as echoes within our minds. This is not a diminishment, but a transformation. The past informs the present, and the present, in its constant flow, shapes the future. The universe does not mourn the passing of a star. It celebrates the creation of new worlds. It does not lament the falling leaf. It anticipates the new bud. This cosmic perspective teaches us to embrace the present moment, not as a fixed point, but as a vibrant, ever-shifting current. It encourages us to find beauty in the ephemeral, to appreciate the delicate balance of existence, where every ending is a prelude to a beginning. The universe is not a static photograph, but a dynamic, living film, and we are privileged to witness its unfolding, even as we are swept along by its current. The impermanence we perceive is not an end, but a continuous, awe-inspiring metamorphosis. And in this ceaseless transformation, we find not just the mechanics of the cosmos, but a profound truth about ourselves, that our own transient existence is made infinitely more beautiful by its very fleetingness. Our calm exploration has covered the profound mystery of why time moves only in one direction. We have journeyed through the fundamental principles of entropy, the irreversible nature of physical processes, and the very fabric of the expanding universe. We've considered the subtle dance of causality, the enigmatic realm of quantum mechanics, and the deeply personal experience of memory. We've seen how the birth of the universe, a moment of exquisite order, set in motion the grand unraveling, the inevitable march from order to chaos that we perceive as the passage of time. Tonight, we have reviewed the principles that govern this unidirectional flow, from the cosmic microwave background echoing the universe's infancy, to the biological clocks ticking within us, a constant reminder of our own transient existence. We've touched upon the limitations of our current scientific understanding, acknowledging that some questions, like the precise origin of the past hypothesis, remain open to contemplation. And in this contemplation, perhaps you can find a deeper sense of perspective. This unidirectional journey, this arrow of time, is not a constraint, but the very condition that allows for change, for growth, for experience. The impermanence we observe is not a tragedy, but the canvas upon which existence paints its most vibrant hues. To understand that time flows forward, that each moment is unique and unrepeatable, can foster a profound appreciation for the present. It is in this acceptance of time's relentless, yet beautiful march, that we can find a deeper peace. So allow this understanding to settle within you, a gentle reminder that you are part of this grand, unfolding cosmic narrative. It is time to rest now. Sleep well. Good night. If you happen to still be awake, you can drift into the next chapter now.